Welcome students once again, and we'll start with next theorems on filters. We'll continue on the chapter of filters. So let us see what the first theorem says today. First theorem of this video. Write down the statement so that you can understand the theorem as well as its proof very well. Let C be a non-empty family of non-empty subsets of, you can say sets of of X, subsets of X, you can say, better you say non-empty subsets of X, then there exists a filter base, on X containing that family C, if and only if C has finite intersection property. That means the finite intersection of any number of members of C is non-empty. So let us see the proof. In the proof, because it is if and only if, we will have to prove the converse part also. So let us start with the straight part first. Let C has FIP. Let C has FIP, and we have to show that there exists a filter base on X containing C. Define a family B containing B subset of X such that B is finite intersection of members of C. That means every member of B is made up by finite intersection of members of C. We will show that this B is a filter base. The first condition for B to be a filter base is that phi does not belong to B, and that is very much obvious by the definition, because every member of this collection B is a finite intersection of members of C, and C has FIP. That means finite intersection of members of C cannot be empty. So this B cannot be an empty set, so phi does not belong to B. Secondly, let B1, B2 be two members of B. We have to show that there exists a third member B in this family such that B is a subset of B1 intersection B2. Now B1 is a member of B, and B contains those sets which are made up by finite intersection of members of C. So that means this B can be expressed as C1 intersection C2 intersection and so on intersection Cn, where these Ci's are members of the family C. Similarly, B2 is a member of B. So B2 can also be expressed as C1 dash intersection C2 dash intersection and so on Cm dash, where these Ci dashes are also members of C. So what is their intersection? B1 intersection B2 is C1 intersection C2 and so on intersection Cn intersection C1 dash and so on intersection Cm dash. That means this intersection is also finite intersection of members of C. Name it as B. So this B is also a member of B because it is also a finite intersection of members of C. So then this B belongs to B such that this B is actually B1 intersection B2. So you can say it is a subset of B1 intersection B2. So there exists a member B in this family which is a subset of B1 intersection B2, which satisfies the second condition for B to be a filter base. So B becomes a filter base in this way. And now let us move on to the converse part of this theorem. Conversely, we suppose that there exists a filter base. Let there exist a filter base B containing C. And we have to show that C has FIP. Let C1, C2, Cn be finite number of members of C. What we have to show that? We have to show that their intersection is non-empty. Now they are the members of C, and C is a subset of B. So that means they are also the members of B. And B is a filter base. If there are a finite number of members of B, then there exists another member B of the filter base, which is a subset of intersection of these. So therefore, there exists B in the filter base B such that this B is a subset of C1 intersection C2 intersection C3 and so on intersection Cn. Now this B is a member of filter base, and filter base contains non-empty sets. So this B cannot be empty. This is a non-empty set. And C1 intersection C2 intersection and so on Cn is a superset of this set. So how it can be empty? So it is also non-empty. We have taken a finite number of members of C and we have shown that their intersection is non-empty. That means C has FIP, and that is what was required to be proved in the converse part of this theorem. Let us have more theorems. There are theorems in which we are concerned with the filters generated by filter bases. So let us see one such theorem as, I'm saying you again and again that you must write the statement of the theorem so that you can understand the theorem very well. Let F1 and F2 be filters generated by filter bases B1 and B2 respectively. Then F2 is finer than F1 if and only if every member of B1 contains a member of B2. Once again, it is if and only if. So we will have to prove converse part as well. So let us start with the direct parts proof. Let every member of B1 contains a member of B2. This is given to us, and what we have to show? We have to show that F2 is finer than F1. We have to show that F2 is finer than F1. To prove F2 contains F1. That means F2 is finer than F1. For that we will have to show that F1 is a subset of F2. We will take one member from F1 and we will show that it also belongs to F2. Let F1 be a member of F1. And F1 is a filter generated by filter base B1. So that means F1 contains some member of B1. So therefore there exists some member B1 of B1 such that F1 contains B1. B1 is a member of filter base B1, and we are given that every member of B1 contains a member of B2. So this member B1 must also contain some member of the filter base B2. So therefore there exists B2 in the filter base B2 such that B1 contains B2. F1 contains B1 and B1 contains B2. By transitivity you can say that F1 contains B2. Now B2 is a member of the filter base B2 and the filter generated by B2 is F2. We know that if B2 is a member of the filter base, then every superset of the member of the filter base belongs to the filter generated by that particular filter base, and the particular filter base generated by B2 is F2. F1 is a superset of member of B2, so F1 belongs to the filter generated by B2, and filter generated by B2 is F2, so F1 belongs to F2. We have taken F1 from F2 and now F1 comes in F2, so this proves that F1 is a subset of F2. That means F2 contains F1, or you can say F2 is finer than F1. So direct part we have proved, and now we will move on to the converse part of this theorem. Conversely, suppose that let F2 be finer than F1. Let F2 be finer than F1, and we have to show that every member of B1 contains a member of B2. Let B1 be a member of B1, and we are to show that this B1 contains some member of B2. B1 is a member of B1, and this B1 is a subset of the filter generated by B1, that means F1. So B1 belongs to F1, and F1 is contained in F2. So F1 is a subset of F2. That means B1 belongs to F2. This means B1 belongs to F2. And every member of the filter is a superset of some member of the filter base. And filter base for B2 is F2 is B2. So that means B1 is a superset of some member of B2. So therefore, there exists B2 in B2 such that B1 is a superset of B2. That means B1 contains B2, or you can say that every member of the filter base B1 contains some member of the filter base B2, and that was the required proof for the converse part of this theorem. Let us move on to some more theorems. There are equivalent bases, and there are theorems based on equivalent filter bases. So let us see one such theorem in this form. Write down the statement of the theorem first. B1 and B2 are equivalent bases, filter bases are equivalent filter bases if and only if every member of B1 contains a member of B2, contains a member of B2, and every member of B2 contains a member of B1. Once again, it is if and only if. So converse part needed to be proved. Once again, so let us move on to the proof. First, suppose that B1 and B2 are equivalent bases. Let B1 is equivalent base to B2. That means they generate the same filter. Let F be the filter generated by these filter bases. That means F can be generated by B1 as well as F can be generated by B2, or you can say that F has filter base B1 and as F also has filter base B2. We have to show that every member of B1 contains a member of B2 and every member of B2 contains a member of B1. We will prove one of them and the second can be proved on the same lines. Let B1 be a member of B1. Now B1 is a filter base for F, so that means B1 is a subset of F. So B1 belongs to F. B1 belongs to F. B1 belongs to the filter, and we know that every member of filter is a superset of some member of its filter base, and F also has a filter base in the form B2. So that means this B1 is superset of some member here. So therefore there exists B2 in B2 such that B1 is a superset of B2, or you can say that every member of B1 contains a member of B2. Similarly, the other part can be proved. And now we will move on to the converse part of this theorem. Conversely, suppose that every member of B1 contains a member of B2 and every member of B2 contains a member of B1. This is given now. This is given now, and what we have to show? We have to show that B1 and B2 are equivalent bases. That means they generate the same filter. Let F1 and F2 be the filters generated by B1 and B2 respectively. What we have to show? We have to show that F1 is equal to F2, or equivalent, you can say that F1 is a subset of F2 and F2 is a subset of F1. We will prove this part, that F1 is a subset of F2. The other can be proved in the same lines. So if we can prove one, we can prove the second. That means we can prove F1 is equal to F2, and once F1 is equal to F2, B1 and B2 will become equivalent bases. So I'm going to prove this one. Let F1 be a member of F1. Let F1 be a member of F1. And every member of the filter F1 is superset of some member of its filter base. So therefore there exists B1 in B1 such that F1 is a superset of B1. But we are also given that every member of B1 contains a member of B2. So therefore since every member of B1 contains a member of B2, there exists B2 in B2 such that B1 contains B2. Now F1 contains B1 and B1 contains B2, that means F1 contains B2. B2 is a member of the filter base B2, and we know that superset of the members of filter base are the members of the filter generated by that particular filter base, and the filter generated by B2 is F2. So superset of B2 belongs to the filter generated by the filter base B2, that means F2. We have taken F1 from F1 and now F1 belongs to F2. This proves that F1 is a subset of F2. Similarly, it can be shown that F2 is a subset of F1. So F1 is equal to F2. That means B1 and B2 generate the same filter, which proves that B1 and B2 are equivalent bases. I'm going to stop this video here. In the next video, we'll have more theorems, more concepts, more theorems on filters. Till then, thank you. Thank you once again.